Good morning, good morning. Can you hear me now? 7 years ago, our forefathers set up, what's next? Set upon this great nation. Oh boy. How we working out there, Chris? Can you hear me now? Test, 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 1, 2, 1, 2.
Yeah.
Okay.
Good start.
All right. Can you expand the screen down here, Chris?
Yeah.
Audio still good?
Here. No, stop. All
right. All right, ready to go? All right. All right, everybody. Thank you for your patience. We're back. Internet gremlins, something happened, but we're back. We're back up and running. So thank you for joining us for week 2 of advanced hydronic training. My name is Jim DePalma. John Resso is running questions today. Eric and Chris are running the back end. So we're going to start off today by asking you guys some questions, or giving you an opportunity. I need the remote there, Chris. All right, thank you. If you guys have any questions from last week, if there are any questions, please type them in. Let us know. We'll answer them. While we're in that process, just let's do some housekeeping. On your screen, you'll see webcam. Please click on that down arrow, hit left. Now your screen should be set up where I'm on the left-hand side. The PowerPoint is in the middle. You will see on your screen 3 hash marks right over here. And you can grab that, click on it, and expand and contract the PowerPoint screen. You can make me disappear, make me bigger, whatever you choose, so you can view this a way that makes you feel comfortable. Also, you've got on your right-hand side of your screen, you've got the window pane there. If you click on the arrow, that opens up. This is where you can type in questions. This is where you can see all your attachments. We sent out a link yesterday with all the attachments. Please make sure you have them available, because we do want you to participate in today's class. We're going to be doing some math. You need to look up and do some formulas today, and you need to also have your TACO catalog in front of you so you have reference pages so you can play along. So let's make sure everybody has that. So if nobody has any questions from week 1, we're going to go on to week 2. All right. All right, so our agenda for today is we are going to figure out how do we design a system. Now, a lot of you are ace mechanics, and you probably have showed up to the job. The boss gives you a box of parts and fittings. The boiler shows up, tells you how to put it in, and you guys go through the process. But what we want to do today is take you through the pre-design, how we do the math to figure out how many BTUs we need for this job and how we plan out to lay out the system. So we're going to go over system design. Then we're going to figure out typical heat load distribution. And generally, when we do this class live, we give options of baseboard, panel radiators, radiant heat, and everybody in the room can kind of decide what they want to do. Since we're doing this via webinar, we're going to decide today we're going to do this with baseboard, but you're going to have two options with baseboard. After that, we're going to go over circulator sizing, making sure everybody understands what information you need to size a circulator properly, then how to read a pump curve, and then within that pump curve, after you've picked your circulator, what is the actual system curve? Because every job you install will have its own distinct system curve. It's kind of like the thumbprint for the system. So that'll be very interesting. And then we'll go over the difference between cast iron and condensing boilers to make sure everybody's up to speed there, because that'll kind of really tighten up what we do today. All right. So first thing is this TACO training takeaways. All right. This is something we got from TACO. It was part of your handouts for today. And this explains how we do a heat loss. So when you do a heat loss, you have to put in information on a room by room basis. We need to know what our design temperature is that we want to attain in that room. Then we need to figure out the infiltration for that room. That means how many outside walls do we have? Is there heat above? Is there heat below? How much glass? How much windows? Is there any outside doors there? And we do that for the whole house on a room by room basis. We have to do that because once we know the BTUs per room, then we'll know how much baseboard or how much radiant or however we're going to deliver the heat in that room, how much of that we're going to need on a room by room. If you just did what's called a block load for the whole house, you'll have a load for the house, but you're not going to have it by room. So it's very simple once you just follow these steps. So what we're going to do is we're doing a pen and paper way, right? Calculator, pen, paper. And it's important that we do this because if you use anybody's heat loss program, Uponor's LoopCAD, TACO's FlowPro Designer, or anybody else's software, RightSoft, this is the information you're putting in anyway. All right, so you need to understand what information it is, and that's what we're going to do now. So first things first, you see it says heat loss. IDT minus ODT equals DTD. Not easy to say at 7 a.m. IDT is indoor design temperature. What do you want to attain in that room? If I was doing radiant, we want to really shoot for 65, maybe 68. If we're doing baseboard or hot air, we're talking maybe 68, 70, 72. So that is important. What is your target, right? So for today, we're going to use 70. ODT, outdoor design temperature. What is the average coldest day of the year where this job is going to be installed? And this is important because we're here in Warren, New Jersey. Wales Derby goes from the southern tip of New Jersey above Kingston all the way out to Montauk. So we cover a pretty wide area. So the average coldest day within our territory will differ depending on where you are. So since we're in Warren today, producing this webinar, our average coldest day of the year here, or temperature, is 14 degrees. So our ODT is going to be 14. So if we take our IDT, subtract the ODT, we get our DTD, which is our design temperature difference. So if you did 70 and you subtracted 14 from it, you should get 56. All right, so if you want to play along, write this down. So 70 minus 14 equals 56. So that's going to be our DTD. And we're going to use that number throughout all these different formulas. So now we have to figure out infiltration. We have to figure out how much of a heat loss we're going to have in that room. So I need to know how many exposures this room has. How many outside walls does it have? It could have one. It could have Do we know when we saw? Oh, whatever, it doesn't matter.
Okay. You're on.
All right, I think we're back. All right, no problems. Internet gremlins again today. All right, so where we were just figuring out for today's room, we're going to have 2 outside walls. So we put in the length, the width, the height of the walls, times the DTD, and then times the infiltration factor. So today's room is a 10 by 15. So please write down 10 times 15. We're going to use 8-foot ceiling height times 8 times our design temperature difference of 56 times 0.018. And if you math that out, you should get 1,209.6. So let's make sure everybody did that again. You want to do this so you can play along and understand what we're doing. So 10 times 15 times 8 times 56 times 0.018 equals 1,209.6. Hopefully everybody's on the same page. Please type in if you're not with us right now. I don't want to leave anybody behind. Let us know. All right. So if you've gotten that far with us, next we're going to do our windows and doors. Okay. So I need to know how much square footage of glass is on those windows and if there's an outside door there. So in this particular example, we're going to have 2 windows, and standard egress windows right now for new construction is 3 by 5. So we're going to take that area, length times width. So it's pretty simple when you have 2 windows of the same size. The height's not going to change, just add the widths together. So 2 3 by 5s become a 6 by 5. 6 times 5 is 30. We're going to take that and multiply it by 56, our design temperature difference, and then we have to multiply it by a U value. How do I find a U value? Well, it shows you on here. To find out a U value, we're going to take 1 and divide it by R. So we are all pretty comfortable with what R values are because our insulation, we have R values for our walls and our ceilings and floors, R values of 11 or 19 or 30. But there's also R values for windows and doors, the most common being an R value of 2. So if I take 1 and I divide that by 2, I will get an R value of 0.5. So I'm going to take the 30, because it's my 2 3 by 5 windows, times 56 times 0.5, and I will get a BTU of 840. So please make sure you do that math. We got our R value of 1 divided by 2. That got us our 0.5. So then 30 times 56 times 0.5, you should get 840. Write that number down. So now next, we go to the walls. So now we're going to go to the walls and we're going to subtract that window area from our walls. So I've got 2 exposures, and it's a 10 by 15 room. So I've got a 10-foot wall and a 15-foot wall. So 10 by 15 is 150. If I subtract 30 from it, I get 120 times 56, our design temperature difference, times the U value for my wall. So in this situation, I'm using a U value, or I'm using an R value of 19 for the walls. That would be kind of standard for today's construction. If you've got 2 by 6 walls, we generally have an R19 in there. It could be higher if they spray foam with 1 inch and then back it up with pink insulation. We can get into R values of 25 and higher. If they spray the whole cavity, that R value can be well into the 30s, maybe in the 40s. So we need to know that. So for today's example, we're going to use 19. So if I divide 1 by 19, I should get 0.053. All right, so make sure you're doing this with me. So take 1 divided by 19, and I should get 0.053. So if I take that math, the 150 minus 30, I take away my windows, that leaves me with 120 times 56 times 0.053, I'm going to get 356.16. Write that number down. What's next? Ceilings and floors. Do I have heat above this room? Do I have heat below this room? Very important. All right, because that means I have 2 more exposures. This particular room is your second floor bedroom. It's over the garage. I've got no heat below. I've got no heat above. So we have to take that into account. So since it's 10 by 15, I'm going to do the same calculation for both the ceiling and the floor, except the U value is going to change. So what is my insulation up in the attic space? It could be from a point, it could be an R value of 25 or an R value of 30. We have to check. We can never assume. So for today, I'm using an R value of 25. That would be ASHRAE minimum right now. So 1 divided by 25 will equal a 0.04. That's going to be my U value to figure out the ceiling. So 10 by 15 times 56, that's our design temperature difference. That number keeps repeating, times 0.04. That's going to give me 336. Write that number down. I'm going to do the same thing for the floor because that's exposed. It's over the garage. The garage is not heated. And I'm going to use an R value of 11 for the floor. That would be the absolute minimum we'd want in that floor for insulation. So if I do that math of 1 divided by 11, I'll get 0.091. So we do the same math. 10 times 15 times 56 times 0.091. That would give me 764.4. So now we've got our infiltration based on our walls, based on our windows, the walls themselves, and then the ceiling and the floor. We add all of that up, and we should get 3,506.16 BTUs. Type in if you're with me so far, if that all made any sense. And if you want me to repeat anything, be very happy to do it. Very important that you're on point with us because it'll make sense as we go forward. If not, I'll be happy to do it again. It's not a problem.
Yeah, a couple guys are asking, go a little slower or write it on the board, but most everyone says so far so good. Got it. What does the U stand for again?
All right. Well, in these formulas here, they're looking for a U value. A U value is representation of how much energy is going to pass through that type of product. Okay. So instead of using an R value, we're looking for a U. All right. And that's how we do that conversion. 1 divided by R will get you a U. When you do any of the software, you just have to put an R value in. The software is going to convert it to a U on its own. But we're showing you the pen and paper method of doing this so you understand why we're doing what we're doing. So was there any part of these formulas where anybody got hung up on? Please type in, let us know. John will let me know. Be happy to go over it again. All right, remember we use 2 exposed walls. That's why we use 0.018. The room size was 10 by 15. We used 8-foot ceiling height. Okay, that's where we got those numbers from. We used 2 windows. Standard egress is 3 by 5. That's how we got our 30 square feet for windows. We had no heat above and we had no heat below. And that's why we had to do our ceilings and floors also. So clear as mud?
We just got a no sound report.
No sound again? Are we good?
Looks, I lost you. Audio.
We lost audio again. Are we good? All right, no, we still have audio.
Okay, here we go. I have sound.
All right. So if everybody's up to speed at that point, the last important formula on this page, and we hammered it last week, and we will use it from this point going forward in today's class, week 3 and week 4, is that universal hydronics formula. GPM equals BTUH divided by delta T times 500. Everything we're going to do based from this point on is going to be centered around that formula. So once we know BTUs, we can figure out our GPM by just plugging it in. The triangle in the T was delta T. In today's project, we're going to be maintaining a 20-degree delta T. And the 500, John showed you last week, was the weight of 1 gallon of water, right? And we're going to raise it 1 degree over 60 minutes. So if you took 8.33 times 60 times 1, we got 499.99. That's how we got 500. That's the number that never changes. We can manipulate the delta T to whatever we want. Once we know our BTUs, we plug that in, and that's when it's going to give us our GPM. So we now know the BTUs for this room, and we can now figure out how much baseboard is going to go in there based on the output of the baseboard. And that's what we're going to do next. Any questions, John? All right, we're going forward. So you all should have, Chris, I don't know if I got control. All right, you all should have your floor plan. Everybody got this as a attachment. So you're going to need this floor plan to play along, because now we're going to start to design our system. And we did the heat loss for the whole house here. And we also did the heat loss on a room by room basis. So you see the BTUs for the whole project are 52,320. And you see we have the BTUs on a room by room basis. So we have to satisfy the load. So now we have to figure out how much baseboard we're going to put into each room. We have to pick a boiler. We have to pick our heating source. So normally when we're doing this live, we give you the opportunity of picking either cast iron or condensing. Since we're doing this via webinar, we are going to pick a condensing boiler today. All right. And then we're going to pick our heat emitter. So you're going to get a couple of options today with 2 different types of baseboard. So first things first, since we know our load, now we've got to pick our boiler. So every boiler manufacturer is going to give you a spec sheet that's going to give you a tremendous amount of information. It's going to give you the input heating. It's going to give you what the boiler can do for domestic hot water if it's a combi. It'll give you an AFUE rating, okay, it's efficiency rating. It'll give you a heating capacity and a net AHRI rating, which if you've been in the business a long time, that was also known as net IBR, okay? And we're gonna understand right now what all these numbers mean. So first off, if you look at this boiler, it's an NTI. All right, we represent NTI. We really like this boiler. It's incredible. This is the TRX. And as you look at this boiler, the jacket, it looks like an appliance. It doesn't look like the boiler you're used to seeing. So this boiler is actually made to either be in conditioned space or unconditioned space, meaning I can have this up on the 2nd floor. I can have this in living space because of its design. It looks like an appliance. And over in Europe, that's what they do. They don't really have basements. So you'll see boilers like this, maybe in the master bathroom, maybe right in the kitchen, okay? But over here, we do have a lot of basements, especially right where we are in Warren, New Jersey. This New Jersey area, New York State area, go out to the island, we have basements. So you see a lot of boilers in the basement. So you can see the heating range on these boilers, 9.4 to 85 MBH. So that particular boiler, the TRX 85, can downfire as low as 9,400 BTUs up to 85,000 BTUs. So this boiler has the ability to step down from 10 to 11 steps. So the boiler can sense outdoor temperature either with a sensor or via the web on internet weather. So you can run this boiler 2 ways. I can either follow the weather by the internet or sense outside temperature with a sensor. If I go with the internet, no need to run an outdoor sensor. So this means my boiler is going to adjust as the temperature outside changes, which is a big deal because we decided that 14 degrees was our average coldest day of the year. But what's really important to understand is we don't always hit 14 degrees every day of the heating season. Our heating season here averages to about 6,000 hours, and we average about 2,500 hours where the equipment is actually running. And throughout the heating season, the daytime temperature and nighttime temperature is going to constantly change. So if we do a boiler like this, which is going to change its output by the change of weather outside, we can be the most efficient and deliver the most comfort at all times, instead of just making one temperature at all time. So we want to take advantage of that. So next you're going to see the heating capacity. And under that 85, it says 79,000 BTUs. And then underneath that, it says net AHRI rating. And that says 69,000 BTUs. What's the difference and which one do I pick? Well, the difference obviously is 10,000 BTUs, but it's really where the boiler is going to be located. So if I went with the heating capacity rating, that means the boiler is going to be in unconditioned space. So you may have this boiler in an unheated basement. You may have this boiler in the garage. So that rating is figuring that we're going to lose 15% of the heating capacity from heat loss off of the boiler jacket and off in the near boiler piping before we can put those BTUs into the home. So if we set the boiler in unconditioned space, we're figuring a 15% loss, okay? Now, if I go and put the boiler in conditioned space, now that basement is heated, or say it is up on the first floor, since this boiler is going to pull outdoor air for combustion, and then we're going to vent out from the side, I could put this, say, on the first floor in a closet, and now I'm within conditioned space. So that means now I don't lose that 15% from jacket loss or piping loss. That's very important for you to know, because that gives you an advantage when you are picking your boiler. Okay, especially when you're looking at cast iron. That can mean from changing from one boiler size to another based on where that boiler is going to be located. All right, so for today, our heat loss for the whole project was 52,000 and change. So that 85 boiler, the TRX 85, is going to be a good choice here, because whether it was in conditioned space or not, I've got plenty of BTU. Okay, any questions on that? I know that was a lot of information, but that's what we're looking at here when we look at this boiler spec sheet. How are we looking, John? We're good. All right, so moving along. So now we've picked our boiler. So what's next? Now we're going to pick baseboard. And you have options in the world of baseboard, okay? Every baseboard manufacturer gives you a spec sheet. And on that spec sheet, based on GPM and water temperature, it'll tell you the output per foot. So if you look at the top here, it says compact. And compact here, we're showing you 4 GPM and 1 GPM. And most of us are all comfortable at 180 degrees input because we're used to cast iron boilers. And if I'm going to move 4 GPM, it's going to give me 620 a foot. And if I move 1 GPM, it's going to give me 590 a foot. But I'm using a condensing boiler. All right, since we're designing this system from scratch, I want to take advantage of this boiler's ability to condense. And if you're not sure what that means, quickly, the explanation is we're going to take the flue gas temperatures and cool them down. So they're going to turn from a gas back to a vapor, back to a liquid. And that liquid is going to rain across basically the boiler's heat exchanger. And in that liquid is latent heat energy that gets reabsorbed back into the boiler. So to make these boilers 90 or 95% efficient, we need to return water temperature coming back to the boiler to be 130 degrees or less. The cooler, the better. It's just going to make the boiler condense even more. And a gallon of condensate is going to be 8,080 BTUs. So I get to reabsorb that back into a boiler. Another way to think about it is if I'm attaining 95%, for every dollar I'm spending to heat my home, 95 cents goes into heating my home, 5 cents goes out the chimney. If it was a standard cast iron, 82%, 82 cents heats my home, 18 cents goes out the chimney. So I want this boiler to condense. So I don't want to use 180 degrees, because if we're going to maintain our 20-degree delta, that means I got 160 coming back. This boiler won't condense. But I could downsize my water temp or lower my water temp. And if I went to 150 and I maintain a 20-degree delta, right? Not enough coffee, sorry, a 20-degree delta, you'll see I'll get either 420 or 400 BTUs per foot. So that would mean I'd have to increase the amount of baseboard per room. So I may have the wall space for that. I may not. Remember, they're going to put furniture in the room. So if I cover everything up with furniture, I'm not going to get good heat transfer. So we have another option. If you look here on the bottom, this is the Synergy baseboard, and this is a high output but low temperature baseboard. So if you take a look here per the spec sheet, at 150 degrees at 4 GPM, this baseboard will give you 597 BTUs per foot. And if I went down to 1 GPM, it's going to give me 567 BTUs of output per foot. That's pretty impressive. That's very close to like high output at 180 degrees. How do they do that on that baseboard? They put more fins on the tubing, and they're larger. So the more surface area I have, the lower my water temperature can be. All right, more surface area, lower water temperature, and I could still attain some nice BTU output. Similar to a radiant floor, big surface area, low water temperature. Because I have so much surface, I can still deliver a lot of BTUs. So for this project today, I want to focus on the Synergy because I really want to make this boiler condense, and I want to take advantage of not having to dramatically oversize my baseboard. So I need you to look at your floor plan, and on a room by room, you have all the BTUs. So we're going to use 597 as the output. Okay. So I want you to take every room and figure out how much baseboard. How do we do that? We're going to take the BTUs per room. We'll divide it by 597. So let's do it together. We're going to do the first room, which is going to be the foyer. So if we do the foyer, and the foyer is 2,240 BTUs. Divide that by 597. So everybody should be clicking or writing it down, right, with your smartphone calculator or calculator. And if I do that, you should get 4 feet. All right, so that foyer with the Synergy baseboard at 150 degrees, right, will equate to only 4 feet of baseboard in there. What's next? We're going to do the master bath next. So the master bath is 1,920. Do the same math, you should get 3 feet. Next room we're going to do is going to be the kitchen of 7,800 BTUs. Do the same math, you should get 13 feet. Next, we're going to do the dining room. Dining room is 4,680. Do the same math, you should get 8 feet. As we're doing this, if you have a question, please type it in, let John know so he'll let me know. Next, we're going to do the bathroom at 2,880. You should get 5 feet. Next, we're going to do bedroom 1, which was 6,240. That's going to equal 10 feet. Bedroom 2 would be next, which is going to be 5,760. You should get also 10 feet. Our living room should be next at 10,400. You should get 17 feet. Master bed at 10,400, same thing. And we are done. All right. Any questions on that? How did we figure out how much baseboard? We took the output of the baseboard and divided it into the BTUs per room. Any questions there? All right. Everybody's good. So now that we have figured that out, and we got this far because we did the heat loss, otherwise we'd be just guessing. Now it's time to zone this. How do you guys want to zone this?
Jim, before you start zoning,
Yes.
quick question here. How does that work with hydro coils? Cooler water temperatures equal cooler air blowing on you. Won't that create customer complaints?
Yeah, it will. You do have the ability. There are companies that do make low temperature coils for higher output. So if you do want to go down that road, you can find them. We represent DHT. They will make coils like that also. So if you do some research, you can find companies that will make coils. If you put like 150 in, you'll still get nice high output. Okay. If not, then yeah, you do have to send higher output there, or delay the fan enough until the coil gets warm enough so we blow hot air on the people. Okay. One of the advantages we have as the TACO guys, we have our Delta T circulator. And our delta T circulator is going to measure temperature and figure, and then the pump will change its speed and maintain whatever delta you want. And when we do jobs like that, we take the supply temperature sensor and we'll hang that in the airstream. So that'll indicate to the circulator what the air temperature is and return water temperature. And what if you want a 20-degree delta, that could speed up the pump much more, increase that flow rate. We can get that coil up to temperature faster. We've got a couple of tricks to get around it, but mostly I would concentrate on getting the proper coil that'll give you a high output at low temperature. Anything else, John?
Good.
All right. So now how do we got to zone this? You guys decide. But I want to talk to you about zones. Zones is comfort, and our job is to deliver comfort. So zoning is not expensive. Zoning is comfort. Please don't be the outfit that wants to get the job and let's knock out the zoning. Let's make the zoning as simple as possible. Let's do this whole floor plan as one zone. That is not comfort, guys. Where would I put that thermostat? What area am I going to put it in? Am I put it in the center of the house? That means the bedrooms, and especially the master bedroom, they're not going to be comfortable. And the people in the master bedroom pay the bills. All right, so zones are comfort. Please don't go into the mode of cut downing zones because we want to be more cost competitive. No. Promote zoning because it equals more comfort. So should we do this as 1, 2, 3, 4 zones? You guys tell us. Type in, let John know how many zones you want to go with. There's no right or wrong here, but just give us your opinion.
I got 3 zones, 2 zones, 3 zones. So far, it looks like 3 is
Okay.
leading the pack.
All right, so we got a couple of 2. We got a majority of 3. So we've got some challenges in this floor plan here. And think of this as a ranch house. So I got no heat above, it's just a ranch, and I got my basement below. If I went with 2 zones, again, I see a problem here. Where would I put the stats? You know, if I split the house in half this way, where am I putting the stat? Am I going to put it in the kitchen? Am I going to put it in this dining room area or this 1 bedroom? All right, that means this bedroom down here is not going to be comfortable. These other rooms really won't be comfortable. And the kitchen's going to be a challenge. Gentlemen, those are cabinets. So somehow I got to get that baseboard in there, and I don't have a lot of room. So that kitchen's going to be a challenge. So I don't think 2 zones is a good choice. If I went 3 zones, I can kind of live with it because we could take the 2 bedrooms and put that on 1 zone. We could take this whole area here and make that 1 zone. And this area here could again be a stretch because the kitchen is going to be an issue. I've got to get how much baseboard in there? What did we say for the kitchen again? Anybody remember? Let's back up. What was the kitchen? The kitchen was 13 feet. All right. As my grandmother used to say, how am I going to get that in there? How am I going to get 13 feet of baseboard in that room? So to me, I see this as 4 zones because the kitchen's a challenge. All right, so I'm going to take the 2 bedrooms. I'm going to make that a zone. I'm going to take the center of the house here. I'll make that a zone. The master bed, master bath, foyer. The foyer is a walkway, but these 2 rooms are very important. Remember, they paid a bill. So I'm going to make that a zone. And we're going to make the kitchen a zone only because it's going to be a challenge. We deliver comfort. We want to make sure they're comfort everywhere. They're comfortable everywhere. So this is the way I decided to lay out the job. And I color coded the zone so everybody can see what we're talking about. So the red zone is the 2 bedrooms, bedroom 1, bedroom 2. Blue zone is your dining, your bath, and your living room. Green zone is the foyer, master bath, master bed. And then the kitchen, since it's a challenge, that is the black zone. And we have to get something in there. And I picked a panel radiator. Now, why did I pick a panel radiator? Well, again, how am I going to get 13 feet of baseboard in there? There's no room. And there has to be a walkway from the foyer into the kitchen. And there has to be a door here to get into that master bedroom. Okay. I don't think we're going to go from the living room to the master bedroom here, though we could possibly. So I may have a back wall here, but let's just assume it's open here. And I'm going to have opening here to get from the kitchen into the dining room to the living room. So I don't have a lot of room. So a panel radiator could be our choice there instead of baseboard. Panel radiators can look very decorative, or they can look very industrial, your choice. We represent a company from Mestec that makes panel radiators. We also represent a high-end company out of Europe called Yaga that makes panel radiators that can look very attractive. So we can just convert that into a panel radiator instead of baseboard. So you can see that we put our baseboard on all the outside walls because those are the coldest areas of each room. So now that we've figured out baseboards per room, and we're doing a panel rad for the kitchen, and we know where we're going to place all these heat emitters, now we have to figure out what is the GPM and the head loss per zone, because you have to tell me now, do we want to zone this with pumps, circulators, or do we want to do it with zone valves? Okay, because we do have, I think 50% of our market's going to do pumps, and the other part of our market's going to do zone valves. You go across onto the island, they're heavy on the pumps for zoning, and you come across here to Jersey, we're more on the zone valve side. So let's look at it both ways. Let's play with it. All right. So if we're going to do pumps, we have to do BTUs per zone. We have to figure out the head loss per zone and the flow rate per zone. So gentlemen, that means we have to guesstimate as best we can the length of each run per zone. You can add up the BTUs per zone, so that's easy. But now we have to guesstimate the length of run per zone. So let's do it together. So if I was looking at the red zone, okay, the red zone BTUs, if I add the 6240 and the 5760, should give me what? Should give me, I didn't do the math, somebody do the math. Let me do it here myself. So if I take that 6240 plus 5760, and I add them together, it's 12,000 BTUs. So at a 20-degree delta, that's 1.2 GPM. How did I do that so fast? I divided 12,000 by 10,000. Or I just took the comma and moved it to the left one spot. So that's 1.2 GPM. I have to guesstimate how long that piping is going to be, all right? So from the boiler side, across, all right, down, back around to the return. And my guesstimation for that was about 84 feet. So if you take a look, we did give you the lengths of the walls. So if you want to do your best guesstimation, but I came up with about 84 feet. So write that number down. So I know I have to move 1.2 GPM for that zone, and I have to overcome 84 feet of piping resistance. We're going to do the same thing per zone. So before we leave the red zone, I have to figure out the head loss at 84 feet. If you go into your TACO catalog, all right, on page 44, you have the head loss formula. Head loss formula says take that run, multiply it by 1.5, multiply that by 0.04, and that'll give you my head loss. So plug in 84, multiply it by 1.5, multiply it by 0.04. So let's do that all together, right? 84 times 1.5 times 0.04, and I should get 5.04. We can call that 5 feet ahead. Write that number down. Now, if my buddies from Stash Lock Plumbing are on today, which they're supposed to be, you guys know this because we've done this a whole bunch of times, okay? Any questions on how we got to this point, John?
Good.
All right, so we're going to do this per zone. So now the blue zone, which was the dining room, the bathroom, the living room, we add up all those BTUs. So let's do that together. 4680 plus 2880 plus 10,400 17,960 BTUs, right? Move the comma to the left one space, you get 1.79. We're going to call that 1.8 GPM because we divided that number by 10,000. Write that down. I'm estimating that that loop, all right, where's my pointer? Here we are. That loop round trip should come to about 98 feet. So plug that number into your calculator, please. 98 times 1.5 times 0.04. We should get 5.88 feet of head. We can call that 6. All right, write that number down. Same thing for the green zone. Let's add up all the BTUs. So the green zone is our foyer, okay, which is 2240. And we're going to add the master bath at 1920. And we're going to add the master bed at 10400. And I should get 14,560. Move the comma to the left. We're dividing by 10,000 BTUs. I get 1.45. That's 1.5 GPM. Take that green loop, my guesstimation, right? Just kind of get an idea. You can see the numbers for the walls and everything. Back to the boiler side. At about 103 feet, and if I plug that in, if I plug that in, 103 times 1.5 times 0.04, 6.18 feet of head. Again, we could call that 6 feet ahead. And last but not least, we're going to do the kitchen zone, all right, the black zone, 7,800 BTUs. I guesstimated the round trip there to be about 29 feet. So 78,000 BTUs, move the comma to the left, 0.78. So we can call that 0.8. And take your 29, look, let's back up. Let's take our 29 times 1.5 times 0.04. I should get 1.74 feet ahead. We can call that 2 feet ahead. 1.7 is close to 2. All right, so everybody should have been clicking, writing, and have all this listed in front of them. Anybody have any questions on how we got there? We're good. All right, so now we know a GPM, we know the head per zone. Got to pick a circulator. All right, so we have to pick a circulator. All right, so that's the information you should have. If you didn't, please write this down. All right, so that's the math that we just did. So I'll just give you a minute or two to write that down. Red zone 1.2 at 5, blue zone 1.8 at 6, green zone 1.5 at 6, and the black zone 0.78. You can call it 0.8 if you choose, at 2. So now we have to pick a circulator. So I'm going to give you two choices here. I'm going to give you the 0015E3 or the VT2218. The 15E3 is a variable speed delta P circulator. You get to choose either a low, medium, or high. If I put it at low, it's going to vary its speed out to 12 GPM, which is 120,000 BTUs. How do I know that? I multiplied that 12 by 10,000. We can use our universal hydronics formula in reverse and convert a GPM into a BTU. So that's 120,000. And it'll hold 5 feet of head all the way out to that 12 GPM. If I go past 12 GPM, then we go on the sloping side of the curve. If I go to medium, now it's going to hold 10 feet of head out to 8.25 GPM, which is 82,500 BTUs. And it'll follow that 10 feet ahead curve if we have multiple zones opening and closing. If I go past 8.25, I get on the steeper part of the curve. And if it was on high, it has the ability to go up to about 16 feet ahead, but it's going to follow that round part of the curve. It doesn't vary its speed. If I go with the VT2218, anywhere within this blue green area, it's going to operate. And this will change its speed based on temperature differential. It'll actually measure the temperature of the supply and the return because it comes with two thermistors. And you dial in there, you program in on it what delta you want to maintain. So regardless of the water temperature coming to the pump, that circulator will always try to maintain whatever delta you put in there. So let's go with the 0015E3 for our project here if we decide if we're going to zone with circulators. Okay, so I need to overcome or deliver, I should say, 1.2 GPM, and I have to do that at 5 feet ahead. So go look here on the 0015E3. 1.2 is right up down here. Well, 5 feet ahead is right here. So if you put a dot here and a dot here, and the two lines are going to intersect right there at the 5 foot ahead mark. Zone 1, 0015E3 set on low, perfect. And that's where it's going to operate. That's the red zone. Blue zone 1.8 at 6. Well, again, we're down here, right about there, 1.8, just past that hash mark. And now I'm at the 6 foot of head mark, which is just above the 5 foot line. So you have a decision to make right now. I need to overcome 6 feet ahead and deliver that kind of BTU, based on the coldest day of the year, all right, where I am in that location. And I'm not going to be there a majority of the winter time. A majority of the winter time, we're probably going to be at a 40% output. So if you wanted to set it at low and only maintain 5 feet ahead, for a majority of the winter, that would probably be okay. And if we did hit our design conditions, our delta would get wider than we want. Would that be a bad thing for the condensing boiler? Not at all. Could that affect the comfort in their home? Possibly. All right, so if you wanted to, you could run it there. And if they were complaining of not being comfortable if we hit a cold streak, all you got to do is put it up to medium speed. So now, if it was at medium speed, I would be plotted here. But what's going to end up happening is there's this thing called the system curve, and it's going to be going up this way because it has to. It's physics. And we'll probably end up performing, we will end up performing at the 10 foot ahead mark and probably overpump by 1 GPM. So there, I will be squeezing my delta, but I'm still close. Either way, I'm going to be close to where I need to be. We do the same thing for the green zone, 1.5 GPM, also at 6. So it's really the same scenario. So now I'm going to be right at that dot, at that hash mark here. I need to be at 6 feet ahead, so I can either put it at medium, and again, I'll be performing up here, and I'll probably be overpumping by 1 GPM, squeezing the delta, or I could set it at low. I could set it at low for majority of the season. And then the last zone, the black zone, at 0.8 at 2 feet ahead. Well, guys, we're down here. 0.8, I'm just past that hash mark. 2 feet ahead is here. I'm going to set it at low. We'll end up performing about right there at the 5 foot ahead mark. Again, probably pumping 1 GPM more than I need. Again, I'll be squeezing my delta. But I'm still as close could be. So one circulator, multiple speeds, and I could zone this project all with circulators. But to us here, 52,000 BTUs on this project, that's a lot if I'm going to zone with multiple circulators. Trust me, if you want to do it, I'm okay with that. We sell circulators, we're happy with that. But I could do this easily with just one circulator. We had 52,000 and change as our heat loss. That's 5.2 GPM. So now, if I'm going to do it with one circulator, all I have to do is overcome 5.2 GPM. And we focus on the highest head loss. So our highest head loss would be 6. So if I decided to do a 0015E3 and use one circulator at 5.2 GPM at a head loss of 6, I could either set it at low and it's going to be performing right here, okay? Or if I set it at medium, I will be performing at the 10 foot mark and probably overpumping by 1 GPM. So my delta will get squeezed a little bit, but I'm still going to deliver those GPM as close could be. That's with a standard P pump that's variable speed. Your other option is going with the VT2218. Now, could I use one of these per zone? I could get pricey. To me, I would use this for the one pump option. So still, I'm going to be at 5.2, and my plot would be right there on the pump chart. All right, and then my head loss at 6 feet ahead would be right there. So since this is a delta T circulator, this circulator now recreates a pump curve. So that's where it's going to perform, right there. All zones calling, that is where I'm going to perform, and that's what I'll deliver. So I'm nailing the actual delta T that I want for that system. As zones open and close, it'll change and create a new pump curve. So if I only have 3 zones, it'll move over to about, well, it looks like 3 GPM and still 6 feet ahead, because that's still the highest head loss. And if one of those zones is calling, it's probably going to be at 6. So now I've just created a new pump curve, and that's where it's going to perform. If I've got 2 zones calling, now my GPM comes down to about a half a GPM, and I'm probably going to be at that 5 foot ahead mark. And even if my smallest zone calls, well, I can't go any slower than that curve here. So at 0.8, I'm going to be there, and it has to run at 4 feet ahead because that's its lowest curve. So this circulator allows us to nail that delta T. And remember, since the heat loss of the building is going to change on a day-to-day basis, and my boiler is going to adjust its output, this circulator will adjust its output to maintain whatever delta we program it in. All right, so that's a great option right there. So I'm going to zone this with zone valves, use a delta T circulator. We'll nail the delta T. We will deliver the best comfort on the job. Any questions there, John?
We had a couple questions. You touched on them, and they answered back that they got it.
Excellent, excellent. All right. Hope everybody's having fun, because to me, this is really cool. This is the behind the scenes. How do our systems work, and how did we get there? And the guys that know this are the guys that can really take advantage of this and really design excellent systems and make more profit. So what's next, right? Well, here's something a little outside the box. I'm showing you a radiant manifold, and I'm showing you panel radiators. I don't necessarily have to use baseboard. Panel radiators are a great option. They don't take up a lot of room, and surface area can grow by height besides width, and I can deliver the BTUs at low temperature. But what's really cool here is using a radiant manifold as my supply and return header. Why not? Radiant manifolds, on average, that barrel is 1.25 inch pipe. If you look at your Taco catalog, 1.25 inch pipe can deliver up to 14 GPM. That's 140,000 BTUs. Our project here only needs 52,000. So 1.25 inch radiant manifold, I'm good. I've got plenty of pipe for my supply and return. What's really neat is I got balancing valves here, so I can really fine tune the flow rate. And I have the ability on the return side to add actuators. Actuators are just little mini zone valves. So I can zone on this, purge on this. Now I can run PEX pipe if I choose as my supply piping. So let's say I was going to use panel radiators, I can feed them all with home runs with PEX pipe. Right? Low temperature, nice balancing in a very tight package. Because a lot of times now your boiler rooms are not the whole basement. You get a tiny closet area to stick this boiler room in. And you may have to share it with the home vacuum system. You may have to share it with the electrician, the electrical panel, or whatever else they're putting in there. So that's just outside the box thinking. Think about that. You can use a radiant manifold, and I can really tighten up my near boiler piping. Okay. Now I wanted to talk about that kitchen. The kitchen is going to be a challenge. I've got cabinets in there. I needed to get 13 feet of baseboard in there. I gave you the option of a panel rad, but what about a radiant option? Why not? Why can't I have radiant in just one room? Sure I can. How do I figure this out? All right, so without going crazy, there's charts available. And we got these charts from the Uponor CDAM. We're the representatives. They were the artists formerly known as Worsbo, and we've been doing radiant here for I think 20 plus years now. It's been quite a long time. So how do I figure out how much tubing, what's my supply water temperature, and what size circulator? And what's my method of attachment? You've got up to 7 different choices. So we're going to go from underneath the floor. It's a very common install, and we're going to use what's called joist track plates. So first off, I got to figure out how many BTUs I can actually put into this floor. So we take the square footage of the kitchen, which was 17 by 13. I get 221 square feet. I'm going to divide that into the BTUs of the kitchen because we did our heat loss of 7880. And I get 36 BTUs a square foot. So this is kind of unique because if you look at the chart, I'm going to go to the bottom. We'll look at the chart here. There's 35 BTUs, so 36 is going to be somewhere in the cracks here between 35 and 40. And anything that's in a gray area or a dark area is too high a water temperature based on the floor finish, meaning if it's wood or if it's tile. And you can see on the left-hand side of that chart, it gives you a room temperature. What's the set point that we want to maintain? So this is where we can get into an interesting discussion. If we were live in person, I could quickly poll the room. So if you want to type in your answer to John right now, I'd appreciate it. What room temperature would you design this radiant system for? Would you go for 65? Would you go for 68? Would you go for 70? So quickly type in what temperature you think you should set that room temperature for radiant heat.
Seeing 67, 68, 70, 68 seems to be the most common one.
Okay, how did I get that outlier at 67? How did?
Yeah, there's one at 67.
It's not that chart's not there.
It's a unique guy.
Yeah, he's special.
Yeah, it's
All
a
right.
unique guy.
Do we know that person?
Yes, you do.
Oh, okay, great. I know it. Then he's just playing with me. All right. Now, believe it or not, in all the training I've had at Worsbo/Uponor for radiant design, and I brought a lot of contractors out there over the years, we were always taught that 65 degrees was the sweet spot. And guys are going to say that's too cold, but think about how radiant works. We're heating the floor. If we heat the floor, it's going to give off radiant energy, and we're going to heat that person up to mid-chest level. We want them cooler from this point up. The heat is not going to stack at the ceiling like it would if it was forced air or even convection off a baseboard. We heat the air, it's going to rise, and it's going to stack at the ceiling. So the warmest part of that room is going to be the floor where the people are standing, sitting, or even lying down. So 65 would be quite comfortable. 68, we've kind of moved to that as our population has gotten older. And, because of maybe some medical issues, we need to make the room a little warmer for some people, depending on if they're on any type of medication or not. 70 starts to be a pretty warm, radiant room. And if the surface temperature gets too high, people's feet will start to sweat, even if they're wearing shoes. Okay? So I'm talking about this because this room poses a problem. So let's look at this. If I'm going to go at that 36 BTU mark per square foot, and I go for 68, I'm going to be up in this somewhere between 86, 87, 88 surface temperature. For tile, 85 is the maximum before we deliver uncomfortable situations, sweaty feet. For wood, I'm not going over 80 degree surface temperature. The RPA will tell you 82, or Uponor is going to tell you 80. And depending on if it's wood floor, water content of that wood floor, it's going to swell, it's going to expand, it's going to contract. All right. So we use 80 degree surface temperature as our governor, so we don't cause any damage to that wood floor. So if I'm going for 68 and I'm going to be in that area here, I'm above that 80 degree mark, so I'm not comfortable with that. If I decide to go to 35 BTUs a square and I go to 60 and I'm at 85.5, half a degree, I could live dangerously on tile. It's not going to hurt the tile, but it definitely is going to make for a warm floor. So let's think about this. If I go and I decide to go with 35 BTUs a square, I will be short BTUs. I'd have to make up that difference. So I could make it up with that panel rad that we did decide with earlier, except it would be a smaller panel rad. So if I took the square footage times 35, okay, if I took the square footage times 35, that's going to deliver 7,735 BTUs. I'm short, gentlemen, but not by much. All right, so some guys would live dangerously and not even worry about that supplemental heat. Other guys were going to want to do it, so I could do it with a small panel rad. That's one way of looking at this, okay? So you have to be very conscious of surface temperature based on floor finish. I hope that made sense. Any questions on that, John? One question just came in. All right, John's figuring out that question. So as we're waiting for that, I'm going to move on.
So they want to know what you would do with the unfinished basement ceiling. I think that's right where you're going. So,
okay, well, my tubing is going to be under there. My joist track plates are going to be under there, and under radiant heat at all times. I don't care what kind of install it is, you have to put insulation. So since we're going to do joist track are steel tracks, about 4 inches wide. Oh, I think they're 48 inches long. And we run them down the length of the bay. And they're right up against the subfloor. And we're going to snap our tubing into those joist tracks. So then I have to insulate, and I insulate right up against the subfloor. There's no air gap when you're using any type of panels or plates, I should say. All right, so we're going to insulate under that kitchen floor. If we don't, the BTUs are going to go up and down. All right, everybody see that? The BTUs will go up and down. So what will happen is we'll be fine on a mild day. And then boom, overnight we hit design temperature or even less. And now that room can't keep up because I'm losing BTUs to below. So we always insulate under radiant. And the minimum I want to see is R11. All right, that's pink insulation, R11 as the minimum. And make sure you, at the end of the bay, at the face of the joist there, at the floor plate of the building, you make sure you've got insulation there so we don't lose BTUs out at the end of the bay. I hope that answered that person's question.
you hit spot. Also, gentleman put up here about kick space heater.
Yeah, we can do kick space. We represent them. I've sold millions of them from my time here. I'm moving air. And, you know, there's really no control over the fan. It's basically at low or high. So I could be blowing a little cooler air until that coil gets up to temperature. There is an aquastat on there, but I don't know. And they tend to be a little noisy after a while. So I like the radiant because it's silent and it's comfortable. It's what I have in my own home for my kitchen. All right. And when you're barefoot in the kitchen and spending a lot of time there, it's really wonderful. It's a great option. It's a great option. But a kick space would work too. And a kick space could be that supplemental heat. And that's another option. All right. So we got to figure out.
So vapor barrier, back to the radiant under the floor. Vapor barrier.
Nope.
No insulation. Just run. This is for ceiling. Sorry, not floor, ceiling. Vapor barrier or not on insulation in ceiling.
Are we putting the radiant in the ceiling?
In the ceiling, yeah.
If you're going to do it in the ceiling, it's actually reversed. And we could do it with the joist track. We would probably do that more with quick track. So the quick track would be screwed up to the ceiling, and they would put the sheetrock up against that. And then you would put insulation on top of that. No need for a vapor barrier. You just put the insulation on top of that. All right. And there, it's not going to be an R11. You're going to have probably minimum 25. You're going to be 30 or higher. Okay. All right. But I'm glad that person asked that question, because radiant ceiling is another great option. If I've got a lot of traffic, meaning I got a lot of furniture, I've got cabinets in that kitchen, maybe I got an island, that takes away available floor space as a heating source. So if it's really, really busy, and this works out really well in bathrooms, especially on second floor master bathrooms, I got the tub, I got the neo-angle shower, I got a double vanity, and this big floor now shrunk down to nothing. A ceiling works out well. I've got no traffic up there. There's no furniture, there's no nothing. I can run higher water temperatures because nobody's going to stand on it. And radiant heat works that way too. It would work out quite well. Right? Just your labor is going to change. All right, so we got to get going here. All right, so we have to figure out now how much tubing. And this chart again comes from the Uponor Sea Dam. And since we're going to use in between the joist bays, we're under the floor, we're going to be 8 inches on center. So it's the square footage of the room times 1.5. So there's my 222, that's my square footage times the 1.5. That's the amount of tubing I'm going to need. That type of tubing as one loop is a little bit too much. Let's break it in half. That's why I'm multiplying it by 0.5. That gives me 2 loops at 165.75 feet. Now I also have to figure liter. That means my manifold may not be right under the kitchen. The mechanical room may be more in the center of the room, or maybe on one end of the basement. So that means I'm going to have tubing. If I'm going to put my manifold in the mechanical room, extra tubing coming to the room before I enter the room. So just for this example, I'm going to say it's a 10-foot leader. But that means it's 10-foot supply, 10-foot return, so it's a 20-foot leader. So now each loop gets an additional 20 feet. So now we're talking 85-foot loops. Now I got to figure out how much joist track panels to put in there. And guess what? We've got a formula for you here. So we take the active loop length. So that's going to be 185 feet. And I'm going to multiply it by that 0.2125. And if I do that math, I'll end up with 70 tracks. I did it by 330, you would just double it if you did it by 185, but now I know 70 tracks. So now we know how much tubing we need, how much joist track we need. All right, it's going to be 2 loop, it's going to be a 2-loop manifold. So far we haven't done anything crazy in trying to figure out what we need. We did our heat loss, we know our method of install, we figured out now how much tubing and how much tracks we need. What's next? Water temperature and GPM and head. Okay, so now to figure out water temperature, again, we've got charts. So this chart's based on a 65-degree room, because remember, 68, I'm going to be a little bit too high, so I'm going to downplay a little bit to 65. We'll make up some supplemental heat either with a kick space or with that panel rad. So if I look at the chart, and I'm going to use tile, that's what that R value of 0.5 means. That's a tile, but it could be a wood. You always have to look up the R value for your finished floor. If it was wood and you don't tell us what it's going to be, we're going to use an R value of 1. And this chart's defaulting as the subfloor is going to be 3/4 of an inch. Gentlemen, I've learned this lesson the hard way. Never assume that it's always a 3/4 sub. That is code. But if it's an older home and maybe they've done some renovation and maybe they wanted to level out some floors because maybe they did some mud with tile in some other rooms, and to level out the floor, they put another layer of sub down, we need to know, because that's going to change the R value or the resistance that we have to overcome. But for today, we're going to use that 3/4 sub. So if I'm going to use tile, and I got BTUs on the side here, so 35 is going to be right about here. That's where it crosses, and I go down here. It gives me 2 water temperatures. All right, so if I'm right here and I go down, I'm probably going to be at about 135 degree water at a 10-degree delta. And if I go to a 20-degree, I'm probably going to be at 140-degree water. So pretty simple how we figured out the water temperature, okay? Any questions on that? Everybody comfortable with that?
Would the temp setting still be 65 degrees with the ceiling radiant?
No, I can go with,
You could go whatever.
I can go with whatever I want, because again, I don't have to worry about anybody standing on that ceiling. Now, we do have some limitations, and off the top of my head, I cannot remember what they are. But, you know, I can get the ceiling surface temperature pretty high, but then we do hit a limit at some point. You know what, I'll get that information and we'll just quickly address it next week when we do week 3 so people know. All right. All right. So now we got to figure out what's our GPM, what's the head loss. So I put a whole bunch of charts up here. So again, the flow chart is from the Uponor C dam. And you can see that I got BTUs per square foot on the side. So 35 is right there, but ooh, we do have 36. So if I went 8 inches on center at 36, I'm going to multiply by 0.00486. Okay. And when I do that, that'll come up with my GPM. I did that math. It comes up to, and it's based on the loop length. All right. It comes up to 0.9 GPM per loop. I got 2 loops, and GPM is cumulative. So if I add those 2 numbers together, it comes to 1.8. So I got to move 1.8 GPM. Now I got to figure out the head loss. So I have to go to a PEX pipe chart. I can't use a copper chart because the inside diameter of PEX is smaller than copper. So I got to use a PEX chart. So I find that GPM. So I'm not going to do 1.8. I'm going to do somewhere between 0.8 and 0.9. So 0.9 is not on the chart because both loops are the same. So I don't have to add the head for loop. We just take the highest loop. They're both the same. So if I went here at 0.8, since it's not 0.9, I'll bump it up to that 1. So we take the loop length times that 0.04, and since it's half-inch tubing, that would tell me my head loss. I did the math, and it came out to 7.4. So now I know I have to move 1.8 GPM times 7.4 feet of head. That's what I have to overcome. But one other thing, if I'm going to be using a mixing valve, because remember the rest of the house is getting 150 degrees, I only need to supply here either 135 or 140. It's a 10 degree, 15 degree difference. I don't want to send too high a water temperature in there because again, I'm not going to deliver the comfort. So I'm going to use some type of mix valve. I do have to take that into account for head loss. So since I'm going to move 1.8, I can kind of look at that 1.5. More than likely, you're going to run with a 3/4. That will add an additional 0.42 feet of head. So I'd add that to the 7.4. So there's my GPM, there's my head, and now I can size the circulator. That wasn't very crazy. That was very easy. Now, there's Radiant software that figures all this out for you. And what do you put in there? Room square footage. What's the surface? What's the room temperature you want? We're putting in the outside walls. We're putting in the glass, heat above, heat below, just like we did in the beginning. And it would give you all this information. And if you're using a mixed valve, you would click on that to add the mixed valve. You put the size in. There's your GPM. There's your head. There's your water temperature. All right. If you're going to do a big project, a radiant project, a whole house, reach out to us. We do those designs. We can help you and steer you to an Uponor distributor. Okay. Johnny, any questions?
I answered a couple. We're looking good.
All right. All right. So I apologize for our late start. Just a couple more slides and we will wrap up today. All right. So quickly, what's the difference between a cast iron boiler system and a condensing boiler system? Is cast iron really non-negotiable today? Is there really any way we can make these systems better? And we can add outdoor reset to it. We're the Taco reps. Taco makes a whole package of controls for zone valves or pumps with the ability to add outdoor reset here. So I could take that boiler system you see there, which could be a 15-year-old boiler system. To me, that's a teenager. It's still got another 10 years. If it was a 10-year-old, it's a toddler. It's still got a lot of time. So if I wanted to make this system more efficient, I can add outdoor reset to it. I can probably take all those mix valves, and even if it was 2 floors, probably keep just 2 mix valves. We don't probably need the third. And we even have mix valves today from Taco that have built-in reset in them. So I can even reset the radiant on this job. So if I add outdoor reset to the boiler, that would monitor the run time of the boiler. I can't change the water temp, but I can change how long the boiler fires. So I can have that change as the outdoor temperature changes. And if I change those mix valves to outdoor sensing temperature mix valves, we can deliver the proper BTUs based on outdoor temperature also. So we can make this system even more efficient. And I can even change those circulators to a variable speed ECM, either a P pump or a delta T. So we can make this even more efficient, okay? But the boiler only knows one thing: to fire to its limit. If we go to condensing, we want to take advantage of that. We want to run the lowest water temperatures we can, and we want the boiler to run off of outdoor reset. Again, the NTI, that TRX boiler, has the ability to run off of internet weather. So that gives you an advantage of not having to crawl into the crawl space to get to the north side of the building, get your wire out there and get your sensor out there, okay? And it's accurate. It's very accurate. It's accurate for right where they live. All right, so that's another option there. So we want these boilers to condense. And the other difference is the venting and the piping. The venting is going to be different. These are 2-pipe boilers. I got to bring in outdoor air. We don't want to use room combustion air. We would need a lot of room area, and you probably have a lot of clutter down there. You probably have your laundry down there. I don't want to bring contaminants into that boiler. And I want to make sure it's going to condense. And the near boiler piping, these are set up as primary, secondary. So I'm going to have a loop just for the boiler, and then I'm going to have a loop for the rest of the house. We will go into detail on that in weeks 3 and 4. So that means more circulators just for flow rate purposes. Okay. So we talked about this earlier, or I alluded to it, how often we're going to be at our design temperature. And you can see here on this chart, 80% of the time, we're only going to be at 12%. All right, or I'm sorry, 80% capacity will only be required at 12%. 60% capacity will be required at 26%. All right, we'll be at 40% for 35% or 65 days out of the heating season. So less than 2%, really, less than 3 or 2%, we're going to be at maximum capacity. So doing this heat loss today was important because it shows you how to properly size the boiler. And even if I was doing a boiler replacement, I'm still going through this exercise. Because if the boiler that was there was oversized to begin with, I could take advantage of that and run lower temperature to the existing baseboard and offer Mr. Smith more options. I can offer them a condensing option and make more money, or offer them a properly sized cast iron, still with the outdoor reset, make more money, or just offer them plain Jane properly sized cast iron boiler. We do a whole class on selling, and the more options you have, the more chances you have to make more profit. All right. So again, cast iron boilers, they can last a long time, don't need a lot of maintenance. If they're relatively young, 10, 12 years, that's a teenager, a toddler, we can make them better and they're still viable. Condensing, well, they condense, we know that. We want to make sure we bring back 130 to make them condense. The piping is different. It's primary, secondary. The venting, it's different. It's a 2-pipe system. If we maintain them, they can last 15, 20 years, so they're going to need annual service. This is not a burden, gentlemen. This is an opportunity. A service contract is going to make you money. Mr. and Mrs. Smith, this is no different than your car. I need to change the oil. I need to service this. I'm checking the heat exchanger, making sure things are clean and the venting is proper. That's all we're talking about. No heavy lifting. Using condensing boilers like the TRX 85, an 11-to-1 turn down ratio. That means the boiler can downfire as low as 9,000 BTUs to meet small micro loads. That's incredible in the efficiency and also the comfort. No short cycling. We can deliver the comfort nice and easy, and the cost of operation is much less. What is condensing? By lowering flue gases, we take the gas, which we cannot see, we cool it down. Now that gas becomes vapor. Whoa, what's vapor? Boil a pot, a teapot on your stove. You see the vapor come out. Everybody says that's steam. You can't see steam. It's a gas. That's vapor. So if I cool that gas down, it turns to vapor. If I cool the vapor down even more, it turns back to a liquid. Inside that liquid is latent heat. We want to capture that into the boiler, and that's what a condensing boiler can do. When I do that, I'm capturing a lot of BTUs. We should generally be producing about a gallon of condensate an hour on most of these jobs. A gallon of condensate is 8,080 BTUs, and we're going to reabsorb that into the boiler. Those would be BTUs that would be going out the chimney normally. So if we don't make a condensing boiler condense, you guys are better salesmen than me. You sold a high-end boiler with really neat controls, looks great, and it's going to perform just like standard cast iron. So if we're going that route, let's make them condense. That's why we went through this exercise today. All right. So there's the formula for every 1,000 BTUs of output, you'll get a gallon of condensate per hour. So one other thing with these boilers, I've got to neutralize the condensate and I got to get rid of it. So you may have a condensate pump on part of your job too. And these charts are showing you based on the cooler return water temperature, the cooler it gets, how high the efficiency starts to climb and climb and climb. So think about it. If the majority of the season, we're only at 40% capacity, our return water temperatures could be down here. And look where we're going to be. That's where we're going to be in that high efficiency area. Okay? So it's been a pleasure today to go over this with you. Week 3 will be next week. Week 3, we start getting into our root cause troubleshooting, which is a lot of fun. You're going to use the information that we've been building upon since week 1 and at the end of today. And we're going to give you, John's going to give you scenarios of problem jobs, and you're going to use these formulas that we've been playing with to figure out what's wrong. I'm sorry?
Download the handout.
Oh, yes. Make sure you have the handouts downloaded for next week. We will send you out an email with the handouts. You're going to need them because to get the most out of week 3 and week 4, you want to play along just like you did today. Any questions, John? Everybody good?
We're clean right now.
All right. Again, we apologize for the internet gremlins, but no big deal. We got everything covered. It's been a pleasure and can't wait to see you next week. Thank you very much.